Sangaletti from the University of Seville, and today I'm going to talk about face print, of course, but for 3D printed materials. So this is just a preliminary result that I got so far with my supervisor, Garcia, at the University of Seville, and it's my first part of this. So, okay, before starting, a brief outline of the presentation for today. Since here basically everyone speaks about face fill, Francesco introduced face fill way better than I could do. I'm instead giving you a brief introduction of the 3D print, why everything is using 3D printing right now, and in particular I will give you like an introduction for the continuous composite deposition for 3D prints, which is the main topic of this presentation, let's say. Then we jump straight to the replication of some experiments, the ones that we found most interesting, let's say, from literature, and then we are going to extend the same approach we used in the second bullet for a typical aeronautical and mechanical case, which is the case of the no-penalty tensile test. And then finally we'll draw together the conclusion. So, as I said, brief introduction to 3D printing. Right now, 3D printing is a topic very on hype. Everyone is basically talking about it and using that both in academy and industries. In fact, in the last years, lots of companies, lots of new companies were born, both as far as the typical 3D printing, so the typical PLA deposition, the normal polymer deposition, and the continuous carbon fiber deposition, which is indeed the main topic of this presentation. But what do we mean about continuous carbon fiber deposition here? So, if we just talk about a normal 3D printer like the one anyone can have, I'm planning to buy a new one for example, you can depose PLA with just one nozzle. You have one nozzle depositing PLA, which is normal polymeric material. But when it comes to continuous carbon fiber deposition, things are different. There's only one producer that actually sells continuous carbon fiber printers, which is Norforth, and the replication of this carbon fiber is here. This 3D printer is here. You can see here two nozzles, one to the left, which is depositing the nylon filament, and another one which is acting at the same time, which is depositing the continuous carbon fiber bundle. Of course, when we talk about carbon fiber bundle, we are not talking about a single fiber, because it would be impossible. But we are talking about a bundle of fibers. As you can see here, these are two typical sections for the carbon fiber bundle. The typical diameter is around 300, 350 micrometers. And the thing that has to be noticed is that distribution of the carbon fibers here, which you can see here in white essentially, are not homogeneous throughout the section. But most likely cluster less, they will be more or less clustered along the section itself. Okay, so this was just a brief introduction, and let's go straight to the replication of some experimental results got by some authors in the literature. We decided to consider a paper where the authors tried to understand the mechanical behavior and the crack pattern for a notch tension, or a notch specimen under tension. You can see here the geometry, with two different reinforcement configurations. These two configurations replicates the one that the authors used in the literature. We have configuration A, where there is no reinforcement of carbon fiber around the notch. Here you can see that the carbon fiber bundle is in dark green, while the matrix, which is onyx in this case, is in light brown. So configuration A, there is no reinforcement around the notch. By configuration B, there is a triple layer of reinforcement around the stress concentration point. It's worth noticing that the two configurations just differ from each other by means of the geometry of the reinforcement, not the geometry of the specimen. As far as the modeling is concerned, we are using face fit by means of the UMAT implemented in Abacus 82 formulation, taking advantage of the coupled temperature displacement solver already implemented in Abacus. As Sindhu said, in this case, the temperature is the face field itself. Why using this kind of UMAT? Because it's easier to extend basically the face field formulation to every kind of elements that we can have in Abacus. And as far as material properties are concerned, both for the Young modulus, for the onyx and the carbon fiber bundle, the values were given by the producer of the 3D printer itself, which is Marford. The L has been considered a numerical parameter, and we'll discuss later about the L itself, while the GC, the value of the onyx has been given by literature, while for the carbon fiber bundle, we took some values for some laminates with more or less the same fiber volume ratio, but then we tried also to compare with some solution that I don't remember the name, that Pino from Imperial College actually given for some carbon fiber band. Okay, so here they go the results. So these are the results for both configuration A and B, comparing the simulation and experimental results. The first thing that we notice is that the crack pattern is completely different. In case of configuration A, the crack starts from the notch as expected, and it cuts the specimen open. While in case of configuration B, the crack does not start from the notch, but instead starts from the other side of the specimen. Once it travels and it meets the carbon fiber reinforcement, which is here more or less, it deviates, trying to avoid the reinforcement itself. It travels as long as it can outside in this region, eventually cutting the carbon fiber and leading to failure. As you can see, comparing the simulation results and experimental ones, we see very good correlation both in this case, and especially, we expected this kind of correlation, but luckily, let's say, we got a good correlation also in this case. Here you can see that the deflection is captured, and here you can see the highlight for the continuous transmotion. So, perfect, no. Let's say, good correlation for the crack pattern, but what about the mechanical properties? Here we are comparing both for configuration A and configuration B, the residual strength and the strain at failure for numerical and experimental results. Here we can see that, especially for configuration B, there are some differences, because as I told you, the GC for the carbon fiber bundle, it's being a relatively new material, it's not so trivial to be computed. And being the carbon fiber bundle, the main material that carries out the load during the tensile, if we don't have a good value for that material, it's not gonna give so accurate results. We decided to try with another, we decided to extend this approach to another example, which is the open open side test. The reinforcement configured here, the material properties are the material, and the materials themselves are the same as in the previous case. The geometry of the reinforcement was taken by literature in order to try to compare the crack patterns also in this case. As a consequence of the applied loading, here you can see the comparison of the simulation results with experimental ones. The experimental results are highlighted here, but they are replicated like with red rows also to overlap. As you can see, the simulation is able to catch the part where the first stage of the propagation, the crack starts and it deviates once it meets the circular reinforcement. But then eventually we have a symmetric model in the finite element. So the crack, we have two crack patterns essentially, while in the experimental results we have just one, because maybe some manufacturing defects or something like that. So the crack starts here, it deviates, and then it cuts straight to space. We eventually decided to analyze, starting from the testing configuration that you can see here to the left, 3 other additional configurations, very similar, that differs only a little bit from the first one. A, B, and C. Configuration A is the typical configuration we could get just simply printing and drilling the specimen, so no reinforcement around the notch, no circular reinforcement, sorry. Configuration B has only one layer of reinforcement, circular reinforcement around the notch, while configuration C is very similar to the tested configuration, but here the fibers are basically attached, the straight fibers are basically attached to the round ones. This just to check what could be the influence. The mechanical properties are shown here, the results of the simulations using the phase field modeling. And here we can see that the 2 best configurations are the tested configurations and configuration C, which are the ones with the triple reinforcement around the notch. So this one and this one. Thus demonstrating the beneficial effect that this kind of reinforcement could have on the mechanical behavior of the specimen. Lastly, last comment about the fact that in this case, in case of configuration A, we don't have the crack propagation exactly aligned with the horizontal axis of the hole, because in this case the fiber is cut basically here, so it acts as stress concentration point, leading to extract propagation exactly from that point of the specimen. So, just to draw the conclusions, the V-notch tension test has been replicated, finding good correlation both for the crack pattern and the mechanical response of the specimen. This approach has been extended to the open hole site test in order to check which, let's say, results, which consequences could have different reinforcement patterns on the mechanical reinforcement, on the mechanical properties of the specimen, finding actually a beneficial effect. And of course, what's next? We are currently working on the computation on finding like a good value, especially for the carbon fiber bundle and the GC, in order to get more accurate experimental correlation. We are developing some codes for accurate fiber deposition path in order to optimize the mechanical properties of the specimen given whichever geometry. And eventually we are going to manufacture the specimen that we are testing numerically in order to validate whatever we got. So that's pretty much it. The paper is currently under review by composite structures, so if you want to know more, just check it out. So thank you for the attention.
Yeah, thank you very much, Simone, for that presentation. Other questions?
You're using AB2 formulation, and you said you have considered length scale to be a numerical parameter, but length scale is a function of GC and strength.
Exactly.
So how do you consider it as a numerical parameter?
That's the problem, because if you consider, in this case, given the material properties, if you check, and given also the strength that I didn't plot here in the table, but if you just use the formulas for homogeneous materials given by 82, it comes out that this length scale is wider than the value than this diameter. So actually, if we consider that length scale value, the approximation of the strength that we have is way better than the one I showed you right now. But we just wanted, I just wanted to stress this point out in order to find maybe solution to this problem, because using a length scale which is lower than the diameter of the bundle, we don't get exact results, but we get like something which is considered physical. While if we use a length scale which is wider than the carbon fiber bundle itself, we got more accurate results in terms of residual strength and strain failure, but we wanted to not to use something, a length scale which was higher than the fiber bundle itself. That's the main reason.
So you are considering it to be a numerical parameter. And have you considered the effect of residual stresses?
No. It's like we are considering just a brittle analysis, since for this kind of structures, the behavior, especially when the carbon fiber is aligned with the direction of the loading, the carbon fiber brings all the load, let's say, so the behavior is basically brittle. So you just have a small deflection, but no.
Okay. Are there some more questions? Please.
Thank you for a very nice presentation, Simon. I'm a little concerned about the material properties, because continuous carbon fiber is not isotropic. So
Exactly. The problem is that here we are simulating a bundle, which is this. So the only material parameter, this value was given directly by the producer, okay? But this value, we are trying to compute like in the most correct way possible, using some analytical formula.
Even in the elastic properties, because we have more than one in different directions, because the fiber is not isotropic. The presence of the fiber.
Yeah, sure. So you mean if you load this thing, is this direction? It's gonna break.
No, not really, because in that direction maybe it's okay. We can consider isotropic, but when the fibers are around, it's definitely not isotropic.
Okay. The problem is that still it's correct, of course, but I don't have a clear answer. These values are like tested directly by the producers. So giving this as a tensile loading and being this value tested for a tensile test directly on the fiber itself, this is so far the most accurate value I feel like giving you right now. It needs, of course, more testing, especially when it comes back to it. We don't. Look forward to it.
Very short question. About the, I mean, this is deposited by layers. I think all the layers have the same.
No, you have like one layer, one layer that you have this distribution, and one layer of just matrix.
Okay.
One.
But all the layers that have fiber have this, or more or less the same distribution,
Yeah,
right?
yeah. In order to add some problems in case of loading some internet.
Okay, perfect. Thank you.
So maybe just to add on top of that question, another question. I mean, the layers. I mean, you assume a perfect cohesion of these two layers, or is it?
Actually, it was shown, for example, for these results that there are some problems cutting the specimen itself after being produced. There are some troubles also in the cohesion between the two layers. So it's still a topic. That's why this kind of technology is still to evolve to a certain point that everything's complete back. Also, for example, some problems in this kind of structure is that here, maybe you don't see, but there are some voids here. Here there is no fiber nor polymer, which is also, it's quite complicated stuff. So also here in this case you can see the black zone is where there's nothing basically. It's a hole. So we just go for, and this could lead some troubles when dealing with the material parameters. No.
Yeah, because I could imagine that you have two layers and you load the sample, you're perpendicular to that layer structure. There might be some.
Yeah, exactly. That's another issue. That's why most of the numerical analysis were done like loading the specimen in the direction of the carbon fiber deposition, and not out of plane loading. Otherwise, it will lead to of course, to the cohesion of the layer themselves.
Oh, there are some more questions. We have time, so there's no other presentations. So
just for checking, have you checked after the testing if there is plasticity, like the unfolding exploded by Sindhu?
The others here I've noticed is small ductile behavior in the layer where there is like only, as I told you, like because there are two layers, carbon fiber and only onyx depositions. There is like a small ductile behavior in the case of in the layer where there's only onyx.
Yes.
But the behavior itself, if you look at the stress curve, in this case it's basically brittle. So there is
in this covered element there is no plasticity in the reinforcement you have put in the V you are doing in this area.
There is no plasticity there.
In the V you are doing just in this point.
In the paper they are not talking about the plasticity here. The V point, but I'm expecting that there is a plastic behavior, especially here where the carbon fiber bundle is not taking all the.
And this plasticity is not considered as starting of the failure or something similar.
We have to, it would be interesting to add also in the model some plasticity in order to check what's actually changing especially in the peak load that the specimen can sustain. So yeah, it's actually it's a good suggestion since we already had in mind to adding for the matrix some plastic.
Yeah, especially this one looks very strange. The failure you are looking, you are finding just on the European side.
Okay, thanks.
okay, one very last question.
Sorry. How did you model this reinforcement around the notch?
Sorry?
How did you numerical model this reinforced in the?
It's like you just take the model in Abacus, you just partition and you assign to the partition two different materials. In fact, that's isotropic. We have two materials here, everyone is isotropic. That's where the main concern of Luis came from actually. But yeah, you see here two different colors, two materials, it's just a partition in Abacus and you assign.
Thanks.
Two material properties basically.
Okay, so that was the last presentation for that session. Let's